Have you ever thrown an apple into the air, then watched it come right back down? Of course you have, unless you're living on the moon, in which case, welcome to Earth. Now here's a strange thing. Every time you throw that apple up, it comes back down. It never suddenly decides to fly and become an astronaut. It never changes its mind. Says, actually, I think I will stay up here. Vertical UAM is what caused all those apples to fall on Isaac Newton that one fateful day. But do you think he understood what vertical motion was from the get go? And why did it cause so many apples to fall on his head? Now, hold on. Let's start from the beginning. Well, over 300 years ago, a certain guy named Isaac Newton was supposedly sitting under a tree when an apple fell on him. Now, whether the apple actually hit his head is still debated. What is not debated is that the falling apple made him think about gravity. Gravity is exactly what causes something called vertical motion. Today, we are going to learn what vertical motion is, why gravity makes it happen, where we see it in life, and finally, we will solve some apple related problems using Gressa, because apparently these apples just cannot stop falling. So, welcome back to the LRC, and today we will be discussing vertical motion or vertical UAM. Now, what exactly is vertical motion? Let's imagine you are holding an apple. You could throw it forward, you can throw it backward, you could throw it straight up. That last one is what we are interested in. Vertical motion is the movement of an object downward. Pretty simple. The important thing is that vertical motion is heavily affected by one force, gravity. Now, like the rest of kinematics, vertical UAM is special in its own ignorance of most other factors of science. Forces like air resistance are assumed to be negligible and non-existent, and all objects from apples to boulders are assumed to be falling at the exact same rate, regardless of mass or weight. It assumes this by putting all falling objects into what is known as a free fall state, wherein any motion of an object is immediately assumed to be under the sole influence of gravity and nothing else. So now, here is something cool. The value of gravity is not the same. On Earth, gravity is approximately negative 9.8 meters per second squared, whilst on the Moon, it is about negative 1.6 meters per second squared. So, if Newton had been sitting under a moon tree, which would already be a situation, that apple would have fallen much more slowly, meaning he would have had more time to move. Now, it is time to put our knowledge to the test. I would highly recommend for you to pause the video right here and check out our first two videos on kinematics, which are our kinematic formulas and kinematic terms. These will prove very useful, especially when solving the next few problems. So now, let's get to it. We will be using GRESA, which stands for providing the given, what we are looking for, the equation we will be using, our solution, and of course, our final answer. So, without further ado, let us begin. The first problem showcases an apple falling from rest. An apple falls from a height of 2 meters. From this alone, we can state our given, which includes the following. The initial velocity at 0 meters per second, as the apple really isn't doing anything initially. The distance as negative 2 meters, as the apple is falling at a height of 2 meters. And the acceleration as negative 9.8 meters per second squared, or a constant gravity. Now that we have our given, we are to move on to the next step, which is our required. For this problem, it has two requirements, one being the time of fall, and the other being the velocity. For now, we are to focus on the time of fall, as it is much simpler. Then, let's write down the equations we'll be using. For reference, our equations will be distance is equivalent to initial velocity multiplied by time plus 1/2 acceleration multiplied by time raised to the power of 2. Now, we apply the equation into our solution. So we plug in all that we know into these solutions. So we are gonna solve for time, which is negative 2 is equivalent to 0 multiplied by time plus 1/2 negative 9.8 multiplied by time raised to the power of 2. After that, we can simplify it further into negative 2 is equivalent to negative 4.9 multiplied by time raised to the power of 2. With that, we can finally move on to dividing both sides by 4.9 as to isolate the variable time. So as we do this, it will give us time raised to the power of 2 is equal to 0.408. Now, if we square root both sides, it will say that time is around 0.64 seconds. So now we put down as our final answer that the apple took approximately 0.64 seconds to fall down. So now that we have solved for the first requirement, we can move on to the second requirement, this time with a bit more resources. So as same as before, we have our initial velocity at 0 meters per second, distance at negative 2 meters, acceleration at negative 9.8 meters per second squared, and now we have our time, which is 0.64 seconds. Now that we have all are given, it is time to move on to the second step, which is our required. For this problem, we are trying to find for the final velocity. So after we have found out that we are trying to look for the final velocity, we move over to the equation that we are going to use for this problem, which for this case is final velocity is equivalent to initial velocity plus acceleration multiplied by time. Now that we know what equation we're going to use to find for the final velocity, it is time to plug in these missing variables with our resources. So, final velocity will remain as our missing variable, which is equivalent to 0 as initial velocity is 0, plus negative 9.8 or gravity, multiplied by our time, which is 0.64 seconds. So, plug all of that into a calculator, and our final velocity will be equivalent to around negative 6.27 meters per second. So, from that, our answer for this final requirement would be that our final velocity is negative 6.27 meters per second. So as always, thanks for watching, and see you next time.